Welcome back. So I am going to continue the previous class, and in the previous class we are talking about the qualitative behavior, and particularly first we are going to focus on linear system, and obviously I am just concentrate my discussion on two-dimensional linear system. And reason I have already told you that because I can represent the trajectory of two-dimensional system in a plane, and in a plane we are able to visualize everything. Okay, and due to that reason, whenever we are talking about phase plane analysis, we are most of time we are just consider the second order linear system or second order nonlinear system. We are also limit our discussion just for the autonomous system, not for the non-autonomous system, because whenever we are talking about non-autonomous system, then one more coordinate system is involved, that is time. Okay, and due to that reason, this part of course is just limited for the autonomous system. So what we found in the previous class, that I have, this is linear autonomous system where x1 belongs to some kind of real number, x2 that also belongs to some kind of real number, and after that what we are going to do, we are going to represent this particular system x1 dot a11 x1 a12 x2 in form of the matrices. So you can see here that I have x dot equal to ax, and here x has two components x1 and x2, and matrix A I am going to consider like this a11 a12 a21 and a22. And what we found in the previous class, that solution of this particular differential equation, because both states are somehow coupled, so that is not trivial, and due to that reason we have introduced some transformation, and finally what we found, that I can able to relate this kind of transformation with eigenvalue of this particular matrix A. So if you calculate the eigenvalue of the transformed system or original system, both are exactly the same. Okay, and if we are able to select this M, it is possible to show that M here is 2 cross 2 matrix. So 2 cross 2 matrix. So you can see that I have one column, and after that I have second column. So if you see carefully, then I can also able to calculate the value of M. M is somehow some kind of transformation. So it is not difficult to find the transformation. What you can do, you can calculate the eigenvalue, and corresponding to each eigenvalue I have a eigenvector. So you can just find the eigenvector. So I have, since I have two eigenvalues, so I have two eigenvectors. So just you can keep eigenvector here. So in that way you are able to find this particular transformation also. Okay, so somehow whatever transformation I am going to apply, that is nothing but eigenvector, and it is possible to show that eigenvector is somehow invariant whenever you are applying the transformation. So just you can fix, so eigenvector of a matrix, I have some kind of a matrix, and if I am in coordinate system of x, then it is possible to show that in z coordinate also that remains invariant. Okay, scaling is different, scaling is change by this particular amount, but that remains invariant. So, and due to that reason, in the previous class, first I have plotted everything in the coordinate of z1 z2. So I am assuming that z1 and z2 are orthogonal coordinate, and after that just you can see the direction of eigenvector. So here I have eigenvector. So now new basis I can express in terms of eigenvector and v1 and v2. And what is basic idea? Basic idea is like this. So suppose if you have certain coordinate system and if you multiply with some matrix, then what happens? Matrix creates some kind of rotation, and you are able to see from here also, from this analysis, that initially I have graph or I have trajectory like this, okay, in two-dimensional space. But after applying this transformation or by multiplying with some matrix m, you can see that rotation comes into picture, but origin remains the same. I have already told you that why origin remains the same in the previous class. So somehow you can also visualize matrix which is going to perform some kind of rotation. So matrix multiplication is nothing but rotation that creates some kind of rotation. So that is the another geometrical picture of the matrix multiplication. And what we found that eigenvalue in previous class, that suppose that if v is some kind of eigenvector, then it is possible to show that m v equal to lambda into v. So what is one of the important property, that suppose in my some space I have some kind of vector v, and if I multiply with some matrix, then what happens, that whatever this vector, that remains the same, just they are scaled by lambda. Okay, so actually this vector is not going to change, and this is not property of all vector because this is eigenvector. So eigenvector only has this kind of property. So I have some kind of a special vector inside the space after multiplication with matrix that remains the same. So somehow I am connecting here linear algebra and whatever analysis we are doing, and due to that reason people are telling that if you are dealing with some kind of linear system or non-linear system, so you have broad idea of abstract or linear algebra is required. Okay, so up to here anyone has confusion? So previous class what we found, that here behavior is like this. If both eigenvalue is negative, and this eigenvalue is nothing but eigenvalue of a, and if you see carefully, then a is nothing but this matrix a. So if you have linear system, then, and if you have to talk about the stability, okay, stability means behavior near the equilibrium point. Okay, and here we are able to plot graph in whole space. I have already told you that what is the reason, because linear system is very beautiful property. Whatever local behavior, same kind of behavior I can extend for whole space. Okay, so just I have to see the behavior near the equilibrium point, same kind of behavior that is preserved by the system if system is linear, but that is not the story in case of non-linear system. Okay, so if you have to check that whatever equilibrium point that is a stable node or not, then now there is no worry about the solution. Just what you can do, you can see the a is nothing but also interpreted as a system matrix. So suppose if you have some system and if you remove the control action, and whatever matrix or open loop system you can interpret like this, or after designing feedback whatever system comes into picture. So what you can do, you can just check the eigenvalue of this. Okay, so what basically I am telling, suppose if you have force system ax plus bu, so you can design u equal to kx, and after that also you are able to do same kind of analysis because your system is now like this. So you can just check that whatever this matrix a plus bk, if their both eigenvalue is negative, then I can claim that whatever equilibrium point of the system, that is nothing but a stable node, or also people are telling nodal sink. Anyone has confusion on this? So system stability is just can be inferred from the eigenvalue of the matrices. That is the main message. Okay, Now let us come to the second case, because I have already told you that if I have some matrix A, then I have several situations. It might possible both eigenvalue are real, both are complex. After that, it might possible in real both are exactly the same, both have same sign or opposite sign. So I have to consider all possible case. So I have just discussed one case. Now I am going to the second case, when where what I am going to consider now. I am going to consider that both eigenvalue are positive. So if both eigenvalue are positive, then curve exactly remain the same, just direction. You can see here that direction of arrow become reverse. Okay, so from again what you can do by the analysis, whatever analysis I have done here, that dz2 by z1. Okay, and what you can do, again you can put lambda 1 and lambda 2, and from here also that is visualized. Another, if you have confusion, then just please look back to the time domain, and here you can see from that is very clear that if lambda 1 is positive and lambda 2 is positive, then what happens, z1 is going to increase with respect to time and z2 is going to increase with respect to time. Okay, so somehow if you plot graph between these two, then it is possible to show that as if you are very far, then what happens that both z1 and z2 are diverging towards the infinity. Okay, if you are in the neighborhood of this, you can see that z1 and z2 both are diverging. Due to that reason I have put this kind of symbol. Okay, and this is called unstable node. Okay, so idea is that you can just again check the eigenvalue of system matrix, and if both are the positive and real, then I can tell that if I start in the vicinity of equilibrium point. Okay, if I start at the equilibrium point, then what is my behavior? Dinah, could you please tell? Suppose I have this kind of situation, and if I start from z1 equal to 0 and z2 equal to 0, then what is my behavior?
At equilibrium point, sir,
So we can move or not move.
you can. We are going to stay in that equilibrium point.
Yeah, so even if I have unstable equilibrium point, but I am going to stay here if you exactly start from here. Okay, but if you deviate a small by a small amount, then what is your behavior? Iram, could you please comment? Suppose if I am not at this point, but if I am in the vicinity of this x z equal to 0, here I have to write because we are in z coordinate. So z equal to 0, then what is my behavior?
It will move away from the equilibrium point,
Yeah.
sir.
So finally I
Okay.
will diverge. Okay, even if any small perturbation you can apply, finally we diverge to the infinity. Okay, but most of time students are thinking that if I have unstable equilibrium point, then if I start here, then also diverge, but that is not the case. Okay, so by the definition of or property of equilibrium point, I am here, but if I deviate little amount from here, then finally I diverge to the positive infinity or negative infinity based on my initial condition. You can see that if you start here, then you can, if your if you diverge in this direction, or if your initial condition that z2 is positive and z1 is negative, then you can diverge in this direction. Okay, so again, a story is like this. If you have some system x dot equal to ax, just check the eigenvalue, and if both eigenvalue are positive, then you have this kind of response. It means that if you start in vicinity of equilibrium point, then you are going to diverge. Now again, you can translate this plot in similar way in x1 and z1, because you know that this kind of transformation is going to exist, and I have told you that this matrix you can construct with the help of the eigenvector. Okay, so again you can plot the eigenvector and just rotate this particular graph, because after multiplying with some matrix, constant matrix, we have certain kind of rotation. Now let us
Sir,
try. Please. Let me.
Sir, by calculating the slope of this plot, we are getting the same nature. Like if z1 tends to 0, then slope is 0. Then how this direction is plotted according to the slope by calculating this?
No, no. Here, from the from the slope, you are only able to comment. After that, seeing the slope, and after that, you have to also look through this kind of solution. Solution means here. From here also you have to look. So both things. And if you have confusion, I have told you that sometime if you have confusion, then please come to the time domain. Okay, from here, because if
Okay, sir.
ratio of lambda 1 and lambda 2, sometime suppose that if this is negative and this is negative, so both create positive. Okay, but if you come to here, then what happens that that in this particular case you can see that as lambda 1 is going to lambda 1 is positive and t tending towards infinity, because t is always implicit inside this. Okay, so sometime means plot is not clear inside the z1 and z2 axis. At that time we are also going to see the time domain response, and based on that we are going to give the arrow. Okay, so
Okay, sir.
and why basically we are doing that, because everything should be satisfied somehow. Whatever relation this comes into picture, that is just due to this. Okay, due to that reason, means in back calculation we have to check that all possibilities satisfy or not. So from this possibly, from this particular relation I cannot comment, then I will check this. Okay, anyone has confusion on this? What curve, nature of curve I can decide from here. From here I can decide the nature of curve. Suppose that if you remove just arrow, then nature of curve is remains like this, as z1 tending towards 0. Okay, and then what happens that slope approach 0 as z1 tending towards 0. So curve, nature of curve means I am not talking about direction. Okay, nature of curve, because whenever we are drawing curve, at that time we are not showing the direction. Suppose that if you have to draw y equal to x square, then we are not showing that what is direction. Okay, so nature, that is called nature of curve. So nature of curve is basically comes from the slope. Okay, and after that, in order to see the behavior, basically we are going to use or take the help of time domain analysis. Anyone has confusion on this? Is it become clear to you?
Yes, sir.
Okay, now let us come to the third case. Okay, so third case, suppose that now I have a eigenvalue, and both eigenvalues has opposite sign, means one is positive and another is negative. So from here also you can able to understand that if one is positive, another one is negative, then what is my behavior. Suppose lambda 1 is positive, so what happens, z1 is going to diverge. Okay, but z2, what is behavior of z2? Z2 is going to converge, because here lambda 2, I am assuming that that is less than 0, means negative. So lambda 2 is negative and lambda 1 is positive. After that, now what you can do, try to plot this relation between Z1 and Z2. So again, what I am going to do, I am going to see the relation between Z1 and Z2. Here actually I have not drive that kind of relation. From here it become clear. You can see here that if I have relation like this, z1 t equal to z1 e power lambda 1 to z2 equal to z 0 e power lambda 2. Again, from here, from this curve only I am going to generalize now, because everything remains the same. This is not going to become alter, but here you can see that automatically this term lambda 2 minus lambda 1, that become negative, because one is positive, so automatically that is negative. Then what happens, z1 is somehow, that is a lambda 2 by lambda 1, that is negative. So now z1 is in the dominator, and if z1 is in the dominator, and let us try to see here from this curve, that here what we are telling that if Z2 Z2 is approximately 0 here in this axis, and suppose if you are consider this point, and after that this point means I am here somehow, so you can see that suppose for time being I have taken this initial condition where Z2 I fix some number, and after that I am varying the Z1, then try to see the response. Okay, so what happens that Z2 here Z1 lambda 1 is positive. So lambda 1 is positive, it means that if initial condition of Z1 that is going to increase, and what about the behavior of Z2 that is going to decrease. Okay, now what you can do, you consider some point here nearby of this. So if you are here, then what happens that in this particular strip that I am here, so and Z1 lambda 1 is positive. So if lambda 1 is positive and if my initial condition is nearby of this, you can just take 0 also, that is not a problem. So in this particular axis what we found, in this particular axis that Z2 equal to 0. So if Z2 equal to 0 means Z2 remains the same, but what is behavior of Z1, that since here I have lambda 1 that is positive. So if lambda 1 is positive, then now what going to happens that if lambda 1 is positive and lambda 2 is negative, then Z2, since Z2 is negative, so what happens that Z1 is 0, so this remains 0, but Z2 is going to decrease. Okay, because in this axis, in this particular axis Z1 equal to 0 and Z2 is non-zero. And what we found that Z2 and lambda 2 are connected and lambda 2 are negative, and due to that reason you can see that here Z2 remains, Z1 remains the 0 because multiplication of any quantity with 0 that remains 0. Due to that reason I have drawn this kind of curve. Okay, now either by symmetry or also you can do similar kind of analysis. Now in this particular axis what happens, Z1 equal to 0 and Z2 is non-zero, but that is now negative. Okay, so now what happens that again that is going to tend towards 0. So due to that reason I have plot like this. Now let us come to this axis, exactly on this axis. So what happens in this axis, now Z2 equal to 0, but Z1 is non-zero. So if Z1 is non-zero, then you can see that Z1 is going to increase, but Z2 is going to remains the same. Then what is direction? What do you think? What is direction? Towards the equilibrium point or away from the equilibrium point? Anyone?
Away from
Away from the equilibrium point. And similar kind of property I have here. So I think that these 4 points is not confusing to you. Now you can see that since you can start anywhere, so what happens, Z1 is going to increase because lambda 1 is positive, and due to that reason now I have this kind of curve. Okay, and one more important point you can see here, from that calculation also Z1 in the denominator. So Z1 is never exactly equal to 0, that is always this kind of curve. So another way what you can do, you can take these two equation and try to plot it. Okay, so after doing plot you are able to find this kind of behavior. Anyone has confusion on this, then please let me know. Okay, now what we found that if I start anywhere in this space, then I have two different kind of behavior. In one direction I am going to converge, but in another direction we are going to diverge. Then what do you think? Suppose that if I start nearby of this, then we are going to remain nearby of equilibrium point, or finally I will diverge. Vinay, could you please comment? Suppose I am going to start nearby of this equilibrium point. If I will start here exactly at equilibrium point, then I am going to remains there. But suppose if I start nearby of this equilibrium point, then what is my behavior? Vinay, are you here? Okay. Silpi, are you able to hear me?
Yes,
Okay. So suppose if I start nearby of the equilibrium point, okay, then
Yes.
what do you think? What is your behavior, or what is behavior of this system?
Oscillating.
No, here I am not talking about any oscillation. You can see here that just I am telling that if you are here, if you are on any axis of this, then you have different behavior. But suppose if your initial condition is here, so again you come back to equilibrium point or going to diverge.
Sir, which point are you talking? Do you
Here I
tell
am
to
talking. Here this point is visible to you. I have drawn. Okay, I will
yes,
change the
yes,
color.
no,
Okay, I will change the
yes,
color. Then things become okay. Now are you able to see this point?
yes, sir.
Okay, then what is behavior?
So,
Any
it's
other?
going to converge.
Iram, could you please comment?
sir, it will diverge because one of the state
Yeah.
is
It is diverge. Okay, means you can see if you start from here, then they are coming towards this axis below. But what happens? Finally, you can see that I have this kind of force. So finally, I cannot touch because some kind of hyperbolic structure I have. So finally, I will diverge. Okay. So what is conclusion? That if you have one of the eigenvalue is positive, then finally my system is unstable. Okay, so for stability, both eigenvalues should be negative. Anyone has confusion on this? And this point has some special name, and that is called saddle point, because we have converging behavior in one direction and diverging in another direction. But overall, I am going to diverge. Anyone has confusion on this? Ankit, are you here? Ankit? Okay, I will check. Okay, Rajesh.
Sir, no doubt, sir. Understand.
So, are you able to understand?
Yes, sir.
Okay. Now this point has some special name that is called saddle point. Okay, so we are able to see that curve is hyperbolic. So it looks like that in one direction we are converging and another direction we are diverging, but final behavior is diverging only. And again, by the same analogy, you can again plot eigenvectors, because eigenvectors, I have already told you the property of eigenvector, and you can draw the curve. Okay, and why rotation happens, we are already understood this point, that whenever matrix multiplication comes into picture, then rotation comes into picture. Okay, so all I have already discussed two cases. So what we have seen till now, that if both eigenvalue that is negative, then what happens, that I have some kind of behavior that is called nodal stable behavior. Okay, and suppose if I have both eigenvalue that is positive, then what happens, I have some kind of diverging behavior. Okay, so trajectory is going to diverge to the infinity, and that behavior I have given name unstable node or nodal. And after that, if both eigenvalue has not the same sign and real, then what happens, that I have saddle kind of behavior. So trajectory looks like hyperbolic. So in one direction we will converge, another direction we will diverge, finally we are going to diverge. Okay, so now Iram, could you please comment that if I have some system, I am going to write the system x dot equal to ax plus bu. Okay, and suppose if I design some kind of feedback control kx, then how to tell that this, so you can see that system remains linear bk into x. So could you please comment that how to select k such that this x is tending towards 0 as t tending towards infinity. And suppose if you have just second order system. Iram, could you please comment?
Yes, sir, such that the eigenvalues of a plus bk is negative.
Yeah, strictly negative, then only I can comment. Okay. Anyone has confusion on this? I will check other possibility in the next part of this lecture. So just I have to check that a plus bk, so you can select any gain, and after that just you can check the eigenvalue of this. If both are strictly negative, then I can tell that this system is nothing but that is stable. Okay. Suppose I want to introduce saddle behavior inside this system, then how to select k? Baby Dana,
Yes,
suppose
sir.
intentionally I want to introduce some kind of behavior of equilibrium point x equal to 0, and I want now saddle kind of behavior, then how to select
So
k?
eigenvalue of a plus bk matrix should be opposite to each other.
Yeah,
Then
opposite
only
to each other. So just you have to do that, because we are just consider. So in this way, if you have linear system, then you are able to introduce different behavior by applying some kind of feedback control. Okay, that is the basic idea. Anyone has confusion on this? No, whatever question I have asked to Dina and Iram, anyone, then please let me know. Okay, now let us come to the another possibility. It might possible I have both eigenvalue that is complex. Why I am telling both eigenvalue as a complex? Why not one value as a complex and another one as a real? Sunidhi, could you please comment?
Sir, complex values always occurs in complex conjugate.
Yeah, complex conjugate. So I cannot deny, if one eigenvalue is complex, then second should be complex only. Okay, due to that reason, if we have two eigenvalue, then we are telling that if one is complex, then another one is also complex. Okay, and due to that reason, we have retained eigenvalue in this particular form, alpha and plus minus j beta. So in this form I have expressed eigenvalue alpha plus minus b j beta. Sometimes people are also write I, and here meaning of this is a square root of I. Actually, if you see the mathematics, so in place of j people are using I, and that is called iota. Iota is -1, but some book people are also using j. So so with respect, so if you check the Khalil books, so most of time they are using j, and due to that reason, in order to remain consistent, I have used similar kind of notion. Okay, b here without loss of generality you can assume positive, but even if you will take negative, then also that doesn't matter. Why? Because if you are going to take negative, then this symbol is just change minus plus. Okay, so without loss of generality you can fix beta greater than 0. So here now I have two different case, alpha either positive and alpha either negative, because I have fixed everything. Anyone has confusion on this? Okay, and in the previous class I have told you that if I have this kind of structure, then I can tell that eigenvalue of this particular matrix can be written like this. Okay, so I am also parallelly taking the course of linear algebra. So in linear algebra, I will tell you that why one can express complex number in form of matrices. So some approximately half hour is required in order to tell that story. So for time being, just by hit and trial, you can assume that whenever I have some kind of complex number, then I can represent that complex number in form of matrix also. And how to represent? You can take the real number, real part of the complex number. After that, you can select the complex part of real number with negative sign you can put here, and beta and alpha. So in this way, and in course of linear or means modern control theory, I will clarify this point. Okay, so what we found that if I have system like A, and after that I have system like x dot equal to ax, and again if if eigenvalue of this m inverse that is complex, then this is equivalent to alpha minus beta alpha, and due to that reason, and here obviously I have z coordinate if I do that kind of transformation, and due to that reason I have replaced this. So now what happens, that you can see that after transformation also I have no extra benefit. Why not extra benefit? You can see here again z1 and z2 are coupled, okay, but if you see that both eigenvalue are real, at that time I have complex number equal to 0. So if you put complex number here also you are able to see the same result. And why that is consistent, you can see that if beta equal to 0, then this reduced to complex number, real number, and due to that reason I have just two term and 0 0. Okay, so from here also you can check. Okay, so at that time when eigenvalue is not complex, so beta equal to 0, and then system is decoupled, but here that is coupling is there, and due to that reason now I have to do something, and here solution is oscillatory. Okay, so Silpi, you are telling that in saddle case solution is oscillatory. That is not the case. Okay,
Yes.
now we are going to see that why solution is oscillatory. Okay, so one way always that you can solve this equation, but solution I try to avoid the solution of difficult equation, and due to that reason I am going to come on different coordinate frame. And one of the most beautiful thing inside the mathematics or inside the nonlinear control system, whenever you have some complicated problem, then what you can do, you can leave looking towards the original coordinate frame, try to define some another coordinate frame, and there are standard guidelines to select standard plane. And if you understand the idea of basis from the abstract linear algebra, then you are able to select different coordinate frame. And I will tell you that why that is very relevant, because if you are not able to understand the concept of basis, then you are not able to understand Taylor series, you are not able to understand the Fourier series, Fourier transformation, and you are just going to memorize that, but you are not able to understand. And due to that reason, course on linear algebra is very important. Okay, now let us come here. What I am going to do, I am going to introduce some other coordinate that is called polar coordinate. And in polar coordinate, what I am going to do, I am going to define z1 as a r cos theta and z2 as a r sin theta. Several times during your school time you might have done this kind of things. Okay, and here this r is defined like this, z1 square and z2 square. Due to that reason r is always positive. Anyone has confusion? I have introduced this kind of coordinate frame, and what is my idea, I want to simplify, because what we found, when both eigenvalue are real, then either positive or negative, at that time just by solving decoupled first order equation I can able to get the solution of coupled equation. So similar kind of things I am going to introduce here, but here I have to do something more, and due to that reason I have introduced the polar coordinate. And you can see that in polar coordinate basically we are going to see the same result. So r is given like r squared z1 square plus z2 square. Anyone has confusion on this polar coordinate? Okay, now what you can do, you can take the differentiation on both sides. Okay, so if you take the differentiation on the both side, suppose that I want to calculate d by dt of r square equal to z1 square plus z2 square. So you can see here I am going to calculate d by dt, but this is also function of time, this is also function of time, so obviously this is function of time. Okay, so if you are going to do that, then what you have to do, first you have to take derivative with respect to r and implicit function, and after that dr by dt. Okay, by chain rule you can think like this. So derivative of this quantity with respect to r is 2 r 2r, and after that here dr by dt I have written r dot. Similarly, similar kind of things you can do for here and do for here. So I think that you are able to understand why I have taken written r dot. Anyone has confusion on this? So just you can apply the chain rule, and after that you can come up with this particular expression. So I am going to remove this part because this is obvious. I hope that you all are already well aware about this. And after that, now what you can do, that try to substitute z1 dot and z2 dot, and z1 dot and z2 dot you can see here from this expression, that is alpha z1 minus beta z2 and z2 are this. So same kind of things I am going to substitute here. So that is just a calculation, and after that now just what you can do simplification, and it is possible to show that r dot is alpha into r square, where I have already told you that r is greater than 0, and if r is positive and r is 0 only when z1 and z2 equal to 0. So I am excluding that case. I am telling that whatever analysis I am going to do, that is not true when r equal to 0. Otherwise I cannot cancel r and r from here. So, and that is obvious case because I know the behavior at z1 equal to 0 and z2 equal to 0. If that is equilibrium point, so if I start from there, I am going to stay there. So I am telling that I do not worry about the equilibrium point. I am just going to see the vicinity of equilibrium point, and due to that reason r greater than 0, r is always greater than 0. So I can write like this: r dot equal to alpha r. Now could you please tell me that in this coordinate system, this is first order differential equation or not in terms of r? Anyone? Rajesh? Are you here, Rajesh?
Sir,
So what is order of this equation? R dot equal to alpha r.
first order.
First order equation, and you know how to solve it. It is possible to show that
Yes, sir.
solution remains like this: r0 initial condition e power alpha t minus 0. So you can again see what I have done. In polar coordinate, I have converted second order equation into first order equation, and I know the solution. Okay. Now, whenever I am converting something in polar coordinate, you can see that I have defined two quantities. One quantity is r and another quantity is theta. So I have to also check the behavior of theta. So for that I have defined, so whenever I have defined z1 as a r cos theta and z2 as a r sin theta, so tan theta is z2 by z1, and I have already told you that I do not consider z1 equal to 0 because that is equilibrium point. So I do not worry, z1 equal to 0, z2 equal to 0. So what I am going to do, and here please be careful, whenever I am writing z1 equal to 0, then I somehow I am excluding one axis also. What is that axis? Because you try to see that if z1 equal to 0 and z2 equal to 0 and z1 not equal to 0, that is not just a point, that is whole axis. Because in this whole axis you can see that I have, what happens, that z1 equal to 0. Okay, so what I am telling, that analysis is just true in this part, this part, this part, this part, but that is not true here. Okay, so due to that reason, whenever you are writing something in form of p by q, so please interpret it carefully. After that, you can see that if you take again differentiation on both sides, then you will get this. I think that this thing is very easy. Z1 and Z2 dot. After that, you know that how to take derivative. Okay. After that, what you can do? You can now just substitute the value of Z2 dot and Z1 dot from equation again, and just try to do the simplification. Here sec square theta is 1 plus 10 square theta, and due to that reason I have written 1 plus z2 by z1 square because I know the 10 theta. And if you do simplification, so now again I come to the very good differential equation, that theta dot equal to beta. And I have already told you that lambda, that is eigenvalue, and that is always come in the conjugate pair, and I have fixed the beta greater than 0 without loss of generality. So either you can fix beta greater than 0 or beta less than 0, that doesn't matter, because if b less than 0, then this sign become negative positive. Okay, so beta greater than 0, it means that now I have, and this is constant, some kind of real number, so theta dot equal to beta, so I have some kind of first order equation, and if you solve this equation, then you are able to see that theta equal to nothing but theta 0 and plus beta into t. Anyone has confusion on this solution? Okay, now what happens, again this is a scalar equation, so what we found, in polar coordinate I have just to solve a scalar equation. Now I am going to see the behavior. So I have just two scalar equation and both equation is decoupled now, so I am in very safe side. And after that you try to see here that what happens, that I am plotting behavior like this. So try to understand this. So you can see that R is nothing but in this two-dimensional plane, R square is Z1 square plus Z2 square. So you can also able to understand that similarly I can write like this also. So if you are here, so this is distance from here, so this is radius. Okay, and what we are telling, suppose that I have started from here, and if alpha is greater than 0, okay, so I have two different case. One time you can consider alpha less than 0, and one time you can consider alpha greater than 0. So first case, what I am going to do, I am going to consider alpha less than 0. So now Nidhi, could you please comment that radius is going to decrease or increase? Suppose alpha is negative.
It's going to decrease, sir.
Decrease, it means that somehow whatever radius means, whatever trajectory, that is going to decrease. Okay. Now let us try to see about theta. What theta is going to do, since that is changing with respect to time, and we know that angle is just change from 0 to 2 pi, again they will going to repeat, and due to that reason I have circular kind of motion due to this, but radius is always increasing and decreasing, and due to that reason I have a spiral kind of behavior. Okay, so what happens if I start with larger radius, so finally I converge to the smaller radius if alpha is less than 0, and if alpha greater than 0, then what happens, that if I start from the lower radius, then what happens, finally that is going to increase with respect to time. Theta is always going to rotate, due to that reason rotation comes into picture, and after that I am going out. Why I am going to going out, because my radius is increasing. So in this way what we found, that I have some kind of things as a logarithmic spiral. Okay, and meaning of stability and instability is like this, since we are going to converge towards the equilibrium point, so that so due to that reason this is called stable. And focus, so finally just like ray, that is going to converge to the equilibrium point, so people are have used this word focus. And here I am going to diverge, even if I will start in the any small vicinity of equilibrium point, and that is due to that reason this is called unstable focus. Anyone has confusion on this drawing of curve or anything? Okay, now what you can do, one more important thing here, suppose that alpha, this alpha equal to 0. So if alpha equal to 0, then what is behavior? Silpi, could you please tell me, if alpha equal to 0, then what happens?
Yes, sir.
What happens?
Constant.
Yeah, constant. It means that if my initial condition is here, then theta is going to change, because I know that theta equal to theta 0 into beta t. So theta is going to rotate, but r is not going to change. Suppose if you fix your initial condition here, then what happens? Again you are going to remain inside this. So any point you can take in this particular plane. What happens? You are not going to converge to the equilibrium point. You are going to rotate for all time, and somehow I can interpret that every point in this space has this kind of property. Okay, if you start, you are going to exactly remains to this orbit only. Okay, because radius is not going to change. Anyone has confusion on this? And this is called center. Okay, so what we found, I have some kind of stable node, unstable node, I have saddle point, after that stable focus, unstable focus, and center kind of behavior. Okay, now here it means that I am going to somehow do this kind of motion, and so this kind of motion is also called oscillation. Okay, but you can see that this motion is not going to remain persistent. Suppose that if you fix r equal to something, and if a small disturbance comes into picture, then you are not able to return back to this orbit, you are going to shift to another orbit, and after that again you have similar kind of behavior. So in presence of a small disturbance also, you are not able to persist this behavior, you are not going to remain in one orbit, because orbit is only function of the initial condition. So if initial condition will change due to some perturbation, and even if you can maintain your eigenvalue, that is completely, now eigenvalue, if you see alpha equal to 0, then plus minus j beta, so that is complex. Okay, then what happens, you have oscillation with different radius r0. Okay, and due to that reason one cannot construct oscillator using this concept, because if I want to fix the amplitude of oscillation, I cannot fix, because due to a small perturbation, if that will change, then that will not never return back. And this is the plot in x1 and x2 axis. Okay, now let us come to the third case, that is last case. What happens that if both eigenvalue are equal, it is possible to show I have equation like this. So at least one equation is fully decoupled, you can see last equation is fully decoupled, and then again if you will solve, and if you will plot, so please check it, because first you can solve this, so solution is easy, and after that what you can do, you can substitute z2 here, because I know the solution, so you can substitute z2 here, and after that you can solve the equation. So in this way you can solve the equation, and after that you are able to see the plot between z1 z2. This whole quantity is just a constant, because this whole quantity, no, not just a constant, because here ln z2 is involved. So here z10 and z20 is actually constant, and k into lambda. Just please check this solution ln z power 2, and also plot between z1 and z2. It is possible to show that if k equal to 0, then relation between z1 and z2, that become linear like this. Okay, obviously when k not equal to 0, and try to see what is k here. So basically k is this part. Okay, so if k equal to 0, then I have this kind of behavior, same like this. But if k equal to 1, you can see that behavior is a little bit like this. Okay, but still if lambda less than 0, then all trajectory is going to converge. So I have some kind of nodal kind of behavior, stable nodal kind of behavior, and here what happens that if k equal to 0, then I have this kind of plot, and if lambda greater than 0, then I have unstable kind of behavior. Okay, so these are the behavior of the linear system, and in next class I am going to see that how basically this analysis is useful in case of the nonlinear system. Okay, so it is time to conclude the today's lecture. So what we found in the today's lecture, that if I have some kind of linear system, and linear system, two-dimensional linear system just I am talking about, and in two-dimensional linear system, and here behavior, okay, of, you can also tell that system behavior, because whatever I have linear system, so either I can talk about equilibrium point or behavior of whole system, that remains the same. So I can tell that this system or equilibrium point of the system x equal to 0, that is either a stable nodal or unstable nodal, saddle or center or focus, that is actually decided by the eigenvalue of this matrix A. And due to that reason, what people found that in case of linear system, just there is no need to worry. You have to just concentrate on a matrix, system matrix. And if you have idea of eigenvalue and eigenvector, then you are able to see the approximate behavior in two-dimensional plane. Similar kind of analysis you can extend for any higher order linear system. Now suppose if you have nth order linear system, then and if all eigenvalue is strictly negative, then you can again x equal to 0 equilibrium point is stable. If one of the eigenvalue that is not strictly negative, then that is unstable. So that much you can tell. So behavior in three-dimensional case, I cannot tell that some behavior like focus, some behavior like saddle, I cannot comment much, but at least I can generalize this to stable or unstable. Okay. So till now anyone has confusion? Then please let me know. So what you can do now, in MATLAB we have some kind of standard command, or using MATLAB you can also able to plot this kind of things. So what you can do, please do that kind of exercise, and everyone what you can do, you can take one system and write the MATLAB code and submit one assignment. Okay. And I want to see the all different kind of behavior. You can see the stable behavior, unstable behavior, and nodal stable and unstable saddle behavior, and all different kind of behavior you can introduce. So you can take either you can take this system, some kind of control system x dot equal to ax plus bu, and you can design u equal to kx, and please show me all different kind of behavior and submit it within 1 week. Okay. And if you have any difficulty, then please let me know. So with this remark, I am going to end the today's lecture, and it is time to ask question. If you have any confusion, then please let me know. Anyone? Okay, if you don't have confusion, then I am going to end the today's lecture. Okay.